In this class, we will primarily focus on the ways where a deadlock will occur. So when we say it is a deadlock, I will give you a general example. There was a bridge. There is a person called as A and there is a person called as B who are opposite to each other. So A will not give way to B and B will not give way to A. So obviously A is struck here, B is struck here, right? The same thing. There is a job A, there is a job B, and both of them they are competing for the same device or same resource. So at this point of time, the the two activities they are going to struck. So in general, what we do is we say task manager, control, alt and del button simultaneously in your laptop. Then what you will do is you will select the task manager. Assume PowerPoint is struck. You will select the power pointer and then you will kill the job or you will end the job. So that is one set. You have your Android mobile phone and your Android mobile phone is not responding. What you will do is you will just restart the mobile because multiple processor hang up, it is not working, it is not responding. So these are the ways what we were talking about deadlocks at this case. So we talked about a partial schedule. Let us look into this. Before a lock has been taken up, before a device has to be taken up, first we need to give a lock, and then once an operation has been done, we have to go for unlock. So when it is an unlock, next other people can use the content. But locking, when it is shared, we call it as shared lock. We call it as a read lock. Sorry, when it is shared lock, we call here as a read lock. Multiple reads can happen. But when there is a exclusive lock, when there is an exclusive lock, at this point of time, we can make only a write. So that was the difference. So lock X and lock A. So both of them, they are waiting for one another. So B lock is going to be dependent on this X of lock and X lock is going to be dependent on the B lock. So either T3 or T4, they are not in a situation to release the contents. So T3 and T4, they don't release the locks. So we call this situation as a deadlock situation. When there was a deadlock, the most important thing was there is a possibility for starvation. So two-phase locking, it is not ensuring the freedom from deadlocks. So obviously it goes with a word called as a starvation. So it keeps on repeating, seeing, checking that whether a release of a device will happen or not. It will goes on verifying it. So as the device is not released, so it will wait, and then it starves. So obviously that process we call it as a starvation. So starvation, when it happens, it is going to happen when there was some concurrency happening. When is concurrency happening? When there are multiple processes, they are going to be done at par, then we say concurrency is going to happen. Now, how we can see that the deadlocks can be eliminated. So one, we can cascade the rollbacks so that the two-phase locking will not be taken up and it will be given to a strict two-phase locking. So that is if read needed, then give chance. If write is needed to multiple transactions. If write is needed, only one transaction at a time. So this is the key takeaway, what we need to understand. That's the strict two-phase locking. In strict two-phase locking, if you want to do a write, do only once, only one job at a time. Then we say it is a strict two-phase locking. If we say that I want to go for a read operation, if I want to go for a read operation, then what we are going to say that you should see that, okay, multiple locks can, multiple transactions can do at a time. So that we are going to permit. But there is another chance where we are going to say it is religious two-phase locking. So this rigorous two-phase locking, so it sees that all the locks are going to be held with the DCL commands, either to kill the transaction, either to freeze the transaction. Freezing the transaction as a permanent, we call it as a commit. Unfreezing, we call it as a aborting, etc. So how is these locks they are going to be implemented, etc.? They are going to be implemented with form of the lock manager. They are going to be taken up in form of the lock manager. So at this point of time, the lock manager, he is going to see whichever locks are going to happen, whichever locks are going to not considered, whether they may lock or whether they may unlock. So that is granting of the lock privileges or rollbacking of the lock privileges. So that is going to be taken up. That is where the lock table is going to be implemented. So a lock table, it will tell that which process need to be locked, which process need to be unlocked. So such elements are going to be maintained to the lock table. Thereby we can grant the locking privileges or we can take back the locking privileges. So how are these locks maintained? These locks, they are going to be maintained in form of hashed index table. So the lock tables, what we are going to mention, these they are going to be implemented in form of hashed table indexes. So this is what we are going to say. A lock table is there. So the darkened tables, yeah, they are going to be granted, and the light blue color, they are going to be a waiting state. They are seeing that whether there is a release of that lock so that it can use. So we do have the disk blocks, and in this disk blocks, whether to make a read operation, whether to make a write operation, they are going to happen. That is on 71 or on T8. That sorry, it is on T1 or T8 or T2. So T2 will happen after T1 and T8 are finished. So T2 is in waiting state. So when T1 or T8 releases the lock, then T2 will be granted the lock. So when there is a lock, you can make a read or write operation. So that is up to the device what it needs to be taken up. So the other deadlock strategy in order to preserve the contents. So we just talked about these two contents, that is starvation, etc. It is taken up with the concurrent manager, etc. So we need to see that we can preserve the deadlocks. So when we are going to preserve the deadlocks, we should pull up the system that it will never enter into a state called as a deadlock state. So if I want to see that the system will never enter into a deadlock state. So we must see that whatever transactions are there, all those transactions they can be listed out, and whichever transactions are in waiting state, whichever transactions are using the shared content, etc., that all is going to be taken up, and we get up with a partial ordering, the order in which the locks can be handled. So there the partial ordering is going to taken up. Okay, deadlock has to be happen. So how can I prevent this issue? So how can I prevent this issue means, yeah, you can prevent this issue by using the concept of timestamps. By using the concepts of timestamps, we can even preserve the occurrence of deadlocks. So deadlocks can be prevented by using timestamp. So what is timestamp? Timestamp is nothing but date and time up to millisecond. So what is timestamp? It is date, it is time up to millisecond we are going to write. So which process, whenever a process is created, timestamp is generated. So P1 it came at some 11:10, P2 it came at some 11:11 in this way. So P3 it came at some 11:12. Now I'm going to write a partial graph. So partial graph. So we draw a ordering. So first it should be P1 followed by P2 followed by P3. So in this model we can uh, give the lock management. So that is how we make a mechanisms to see that the order in which locks can be given. Therefore, deadlock will not happen and there is no starvation. Why there is no starvation? Order we have given, we have drawn a wait for graph. It is P1, P2, P3. In this wave only the process has to be executed. We are determining it. So the order will be followed by the DBMS. So there won't be any clash between transactions. So deadlock will be preserved. So that is where the advantage of timestamps is going to come into picture. So while doing up this deadlock, we say with the wound and die, we say with the wound and we say with the wait and die. So when we are going to do the things with the wait and die, it is a segment which calls in the non-preemptive content, and when it is going to be a wound and wait schedule, then it is going to be a preemptive content. So the way what we are going to write will be the words that is with wait and die and wound and wait. So this will be taken up with a rollback here. So these wound wait and die and wound and wait, yeah, they will be purely based on the timestamp base. So they are going to give some specific time. In that specific time the activity was not take up, then it goes with a wait and die concept. So altogether, how to eliminate the concepts from the deadlock prevention was, we need to drop the wait for graphs. We need to drop the wait for graphs. So in this wait for graphs, yeah, we go with some pair, that is G, it is going to stands for the graph, V, it stands for vertex, and E, it stands for edges. So what it is going to tell us which is first transaction, which is next transaction. First Ti followed by Tj. In this way we are going to drop a graph. So here is a system model for drawing up a graph. So we have the order. First it should be T17, then it moves to T18, and then it goes to T20. This is one of an order, and you can see T17 to T19 and T18. So if I'm going to see that T18 has to move up, so it is direction 1 and direction 2, right? So I have paths T17, T19, T18 and T20. The other path was T17, T18, T20. So we are making it as a without cycle. But what happens if we are going to do with a cycle? With a cycle, if we are going to look into this content, then we can say it is from T17 to T18 and T18 to T20, T20 to T19. We get this, and the cycle is going to form out at this point of time. Similarly, you can see T17, T18, T19. A cycle is going to move. So that is where the wait for graph is looking into the scenario. So how we are going to detect the deadlock? Yeah, we have detected the deadlock with the timestamp based strict two-phase locking, and another with uh, strict two-phase locking, and another one was the religious two-phase locking. We made all these entities. Now, are there any other ways where we can go with the deadlock recovery? Means, yeah, you can go with a word called as a rollback. Then we can do with an undo operation. So we go with the rollback. So that is move to the previous state until we find the victim. Until we find the victim, we will move back to the previous state. That is what the deadlock recovery is happening. Next word, an extension version to the deadlocks was to work with the granularity. So when we drop a granularity, we represent the things in form of trees. So one, it says that it is called as fine granularity. Two, we are going to call it as a coarse granularity. So this, it is going to start with the root node, followed by middle node, then it moves to the leaf node. So root node, middle node, and leaf node, middle node, and leaf node. So it moves into different levels. So we are going to organize the data items into different levels, into different hierarchies. That is where the smaller granularity are nested in the larger ones. So at the root we have the larger ones, and at the leaf we are going to have the smaller ones. So this is what the transaction is looking at. So when it is in the lower tree, we have very good concurrency control and good locking hierarchies. But when it is a coarse granularity, it moves from higher entries, that is needs two-phase locking and low concurrency control. So at coarse granularity, we apply the bottom-up approach, and when it is with the fine granularity, we move to the top-down approach. So this is the two differentiations when we work with the locking granularity. So uh, the locking granularity example we are going to mention, the very first level, that is level 1, it is going to be the database, and followed by the area, the part or a chunk of the database, that is level 2. Then we do have a file that's it is going to be some level 3. Then we are going to have some records, that is level 4. So records, they will have some set of fields, so we call them as some still the data items in it. So this is what the granularity of a database architecture is mentioned. So the very first level we have the database. Next was the part of a database, we call it as different tables of a database. And third, the subset, the tables inside the parts, and finally the records, what they are going to work, and thereby they cascade to the root level, to the records and attributes level. So while doing this granularity, again, we apply the locking mechanism. So in this locking mechanism, we have a binary lock. So that is locked and unlocked. So locked, it is represented as 1, and unlocked, it is represented as a 0 item. So we have these two states here, 1 and 0. So it indicates whether the transaction has locked the shared database, yes or no. So that it can be taken up only with the intensive shared, and then with an exclusive option, and then both shared and exclusive option. When it is going with the shared, then it says with a read operation. When it is going with an exclusive operation, it goes with a write operation. When it is going with the shared and intensive exclusive operation, it performs both read and write. So altogether, it can happen from the lower levels and to the higher levels, and again they move from lower levels to the higher levels. So when we are going to call it as a lower levels to higher levels, it affects on the attributes, then to the tables, and then to the tables, and then to the pinches of the database, and followed by the complete database. So that is the hierarchy what it is going to affect. So first it will be done on the attribute, then it will be done on the rows, followed by tables, and then to the database, and then to the DBMS. So this is the way we are provoking attribute, rows, tables, databases, and the the entire DBMS content. So this is how the granularity was mentioning up at this case. Yeah, the other way what we discussed towards the deadlock was that we worked with the timestamp based protocols. So in timestamp based protocols, we will look at the ordering. So when the process, when the transaction created, when the transaction is going to be created, or when the transaction made a read, or when the transaction make a write. So when to make a read operation or to make a write operation on a database, it is going to be ordered with a read timestamp, or it is going to be ordered with a write timestamp. So we will verify this the way the timestamps are considered. If the smaller job is less than the higher job, obviously the smaller job will be given chance to use the database. So in this way, we are going to give some ordering towards the timestamp based content. So larger timestamp, it is taken up with the write operation to be successfully. So in this model, we will give up the write timestamp and read timestamp. So the algorithm we have already taken in the main classes. So the timestamp based algorithm, which it is going to issue a read operation, and followed by the timestamp based algorithm, which it is going to give up with a write operation, etc. So what we are going to see that the transaction with smaller timestamps, they will be followed with the transaction which are taken up after the larger timestamps. Once we see that there is no cycles. So how we are going to see that there is no cycles means we are going to drop a precedence graph. So in this precedence graph, we will check which transaction to be first, which transaction to be next, and the ordering, whether it is read, whether it is write, it is shared, exclusive. So all that model we are going to incorporate the things. So we don't have validated protocol based content for our syllabus here. So after deadlocks, timestamp based protocols, the other part of the content will be the crash management. So before we look towards the crash management, the first thing we need to understand about the failures. So where the error is going to come. So one we are going to call it as a logical error, and another we call it as a system error. So in logical error, yeah, it is taken up with the software, and system error, yeah, it is with the hardware. One it is taken up with the software, and another it is taken up with the hardware. So when we are going to call it as a system crash, there was a failure of the hardware, etc. So that we are going to say a system crash. Similarly, when we talk up with the disk failure, we assume that there is some problem in the disk and it is totally failure in the content. So how we can look this issue so that we can recover the transactions which were lost. So we need to recover the transactions which were lost. So how we can do it? So in order to do that, because a disk has been crashed, the disk has been corrupted due to some hardware error and due to some software error. So the recovery algorithms, they see that at any point of time the loss of data can be recovered. So they are going to ensure that the information it is going to be recovered from failures. So how good or what will be the actions taken to recover from the failure means, yeah, we will work with the acid properties, that is with the atomicity, with the consistency, with the durability, and with the isolation words. So we will see that whatever transactions we are going to make, such transactions they are going to be followed with the same event. So coming to the next word, what we can look here will be the storage structures. So in storage structures, we will highlight up with one, we call it as volatile storage, and two, we are going to call it as a non-volatile storage. So non-volatile storage is an example for the random access memory. Volatile memory, it is an example for the read-only memory. And stable storage, we are going to have the database, and this it is going to be in the secondary storage or stable storage. It will be a part of the cloud. So right now we are working on livesql.oracle.com. So livesql.oracle.com is an example for the cloud storage. So whatever programs were stored, that stored content, it is in the Oracle cloud there. So that is where the storage structure is coming up with an impact. So we have volatile storage, we have non-volatile storage. So when we say it is volatile storage, it is vulnerable to clash, but still we can get the things. But when it is non-volatile storage, we may lose some data, we may still lose some data. So but when it is going to be a stable storage, yeah, we say it is having a property called as durability. So durability in sense that it will makes the transaction to be permanent and be accessible at any point of time, that too for long periods. So another thing was that how data is going to be stored and how data is going to be accessed. So we will draw the hard disk mechanism, and hard disk mechanism, yeah, it is going to have some disks, and we call these elements as blocks, and the storage of the blocks will be on the tracks, and a section of a track, we call it as a sector, right? So we have a hard disk, and hard disk is having many partitions, and we have a spindle here, and this spindle, it is going to rotate it and do some read or write operations for the disk block. So disk blocks, they are going to be accumulated on a hard disk, and they are going to be stored in form of tracks, and a partial ordering, we call them as some sectors, etc. So in general, when we are going to say it is axis of a blocks, so they can be the physical blocks, which we are going to do it in the secondary storage devices. It will be in secondary storage devices. So that is what we call it as a physical blocks. But when we are going to call it as a buffer blocks, yeah, they will be on the random access memory. They will be on the random access memory, and they are going to be temporary. So from the buffer blocks, we need to move them, we need to push them to the secondary storage. We need to push them to the secondary storage. So in order to involve this, we need to have a block movement. So that is, we need to transfer the physical, we need to transfer the buffer blocks, operate it, and then that operation should be committed and made permanent, and thereby they should be moved to the to the standard database. So that is all it is going to be happen from the disk and the main memory. So what operations we can do? We can do the operations called as input, and we can do the operations called here as an output. So coming to the way how the disk blocks are stored, the order in which the disk blocks are stored, we need to have a mechanism, and that mechanism we are going to call it as logging. That mechanism we call it as logging, and logging, it is kept on a stable storage. That is what we call it as some secondary storage content. So this log, it is going to have some sequence of log records, and it is going to maintain all the database updates. So as in a lab, we have a log, that is whoever has entered the lab, whoever has using the system, at what is the system number and what time you entered. So everything is going to be recorded when we are going to enter into a offline lab. So similarly, the transactions, when they are about to start, first of all, the transactions, they will be recorded in a book, and that book we are going to call it as a log book, and that it is going to be stored in the stable storage. So whenever a transaction needs to be started, the first and foremost item will be the TI, that is the transaction number, transaction 1, 2, 3, like that, and then it starts with a command called as start. And after that, it goes with either a read operation, it checks up whatever operations it has been involved. So all the states, the values, the previous value, the next value, the new value, so all those values, they are going to be pushed up. For example, 500 rupees is going to be in the account. Now I'm going to add 100 rupees, so it is 600 rupees. So the 500, we call it as some old value, and 600 we call it as a new value. So 500 I call it as VI, and 600 I call it as VJ. So now I can have a sequence with first it happened with I, next it happened with J. In this way, we are going to make the order of the log sequencing actions what were happened towards the data. So finally, we make a start operation, then we do all the read or write operations. So this is what we call it as begin, and the end operation we make. So the end operation we call here as a commit here. So to make the transactions as a permanent, so that end operations we are going to do when it is finished, we call it as a commit operation. Okay, fine. Now in between, now we want to switch to a other previous transaction. then what we can do is we can go with the undo operation. Okay, after undoing, again we want to move to the state where we came. So that is what we call it as a redo state. So undo and redo, they are going to be totally worked using the log-based recovery content. So for today, we will pause our discussion at this point of time. So in tomorrow's class, we will be talking about the log-based recovery with undo, redo operations, and thereby we will talk about the iris algorithm, etc. So we have 48 students turned now.